Welcome to Tollefson Physics. So what we're going to do is we're going to continue looking at velocity time graphs as a way to solve motion problems. So this is part 3. Hopefully you have had a chance to look at part 1 and part 2. And so this one, every velocity time graph problem is still related to acceleration being the slope and the displacement being the area under the curve. And so in this particular case, we're going to have a known acceleration and a known displacement. So we'll know the slope and we'll know what the area under the curve is. And for sometimes it feels like you don't have enough information to figure out the other two things, which would be the change in velocity and the change in time. Fact of the matter is you do. And so we're going to follow the exact same process that we've been doing before as far as setting it up with a velocity time graph and writing area and slope equations. But now we've got to combine those two equations to get to a final result. And so let's look at this first question here, where we're going to drop an object from a height of 80 meters. We're going to assume there's no air resistance, and we're going to predict the time that it takes for that object to hit the ground, and then the speed that it will be right before it hits the ground. So I'll go with my famous crude drawings. Somebody standing on top of this building, and that object, ball I guess in this case, is going to fall 80 meters. Alright, we're going to start with a velocity equals 0. And so one other thing when we're dealing with free fall, it's written kind of under here, is that acceleration equals the acceleration due to Earth's gravity, and we're going to use 10 meters per second squared to make the calculations a little bit easier. And so, like every other problem that I've shown you so far, we're going to do a velocity time graph, right? The thing is, we don't know the velocity and we don't know the time, but we can still say, oh, this thing's speeding up, right? So velocity time graph is going to look something like that. Yeah, it starts at 0 because I said it starts at 0. And so it's going to take a certain amount of time. I'm just going to call it t, and it's going to get to a certain speed that I'm just going to call v, right? And so what do I know? I know that the area is 80 meters, and I know that the slope is 10 meters per second squared. So how do I use those? Well, like I said, I'm going to write an equation for each of those. So if we think about area equals 1/2 base times height, right? Which really is the displacement equals 1/2 times the velocity times the time, right? Velocity is the height, time is the base. I know x, right? So I'll write in the number in this case. So 1/2 v times t. And I'm just using v and t instead of delta v and delta t because they both started at 0. And so that's one equation, has two unknowns. I can't solve it. All right. So then let's think about our slope, right? Rise over run, which when we look at a velocity time graph, the slope is called acceleration. The rise is the change in velocity, and the run is change in time. I know what a is. A, due to gravity, is 10 meters per second squared. And I'm going to just simplify this to v divided by t once again because the velocity starts at 0, the time starts at 0. I don't like the format of this equation, so I'm going to cross multiply. I'm going to multiply both sides by t, and then I actually end up getting the equation of that line, right? Because if I let the rock or whatever fall for 1 second, it's going to be traveling 10 meters per second. If it falls for 2 seconds, it's going to travel at 20, and so on. So once I figure out the time, I know the velocity. But now what I have is what's called a system of equations. Two unknowns, two equations. So I need to combine these equations. So I'll end up with 80 meters equals 1/2, and then put this in for v. I'll put parentheses around it so we can see that's what v is. So 10 meters per second squared times time times time. And so let's simplify that by combining the t's. Now this looks like an equation that you may have seen before, which is x equals 1/2 at squared, which is valid when the initial velocity is 0 and the initial position is 0. So then we can go ahead and we can solve this, right? So what's the easiest way? 160. So if I multiply both sides by 2, I get 160. Divide by 10, I end up getting t squared equals 16 seconds squared. And then what you do is you take the square root of both of those and you find out the time is 4 seconds. Once I know the time is 4 seconds, guess what? I can go right into here. I could substitute 4 seconds times 10 meters per second, and I end up finding out the speed right before it hits the ground is 40 meters per second. So it all falls together when you're using both the area and the slope definitions of a velocity time graph. Now I want you to try this problem. So for an accident reconstruction, you can determine a couple of things. So a couple of things you can look at are what kind of tires and what were the road conditions. And from that, they're able to figure out the acceleration due to braking of those tires skidding on the road was 5 meters per second squared, and that the car had a skid length of 62.5 meters. So what I want you to determine is what is the speed of the car when it started to brake, because that way we can see if it was going the speed limit or not, or too fast. And then, because we can, let's figure out the time it took to stop as well. So hit pause and give this a try. All right, welcome back. So let's go ahead and solve this. So basically, my crude drawing, so we've got this car, it's going to skid 62.5 meters. We don't know what the starting velocity is. It gets to the end, it's not moving, and we know the acceleration is 5 meters per second squared. So let's go to our handy dandy velocity time graph. And so this time it's something that's slowing down. So we're going to assume that we have a uniform acceleration, draw a straight line. We don't know this initial velocity here. We know the final velocity is 0. We also don't know the time here, right? So this final time we don't know as well. So let's go ahead and write equations. So in this particular case, we're going to have to write a slope equation and an area equation, and then combine the two as a system of equations to actually solve for what's asked for. So let's start with the area equation, right? So area in the case of a triangle is 1/2 base times height. One of the nice things about using a velocity time graph is that shape of the triangle doesn't change. So we, from a physics standpoint, can look at, well, that change in position, I'll just write it as x, equals 1/2 the base is time, which I wrote as final time, but I'll just write it as a t up here, and times that initial velocity in this case. Whereas in other cases it looked like we did final velocity, but that's just the height of the triangle, right? So we can customize for what we are doing. And then what we can also do is look at the slope, right? Slope is so let's just write that. The slope is the acceleration, and that is the change in velocity divided by the change in time. Now I didn't write those deltas because actually in this particular case we know it's slowing down, we know it's a negative slope. Technically final minus initial for velocity is negative as well. So I'm just going to handle the magnitudes in this particular case. Now one of the nice things here is this cross multiplies to a equation, sometimes called a kinematic equation, that you see listed on equations sheets and such. So we're going to use that as well. So let's plug in the numbers that we know for all of this stuff. So here we know 62.5 meters equals the 1/2 times whatever that base time is. So it's from 0 to TF. And what's that velocity? So in this case it's the initial velocity. Over here I wrote it slightly different because then I can substitute it in right away, is the velocity is going to equal the acceleration, which is 5 meters per second squared, times time. And the reason I wrote it this way is I can plug it in there. So when I substitute in that for velocity, I'm going to move the 5 first because I just like my numbers first, and then I have a t times a t, so that's a t squared. Now this looks awfully familiar for another kinematic equation, which is 1/2 a t squared when starting velocity is 0. All right, so then how do we solve this? Well, what we're going to do is we're going to take the 62.5. I think it's easier to multiply that by 2 first to get rid of the 1/2 on this side, so that's 125. and then we're going to divide both sides by 5, and what we end up getting is a time squared of 25 seconds squared. So then what you do is you take the square root of that, slide that up a little, so the square root of that is 5 seconds. So it took 5 seconds to stop. Okay, well, part of the question was, well, what was that starting speed? All right, so the starting speed, let's do that in blue here. So the starting speed, I have my velocity equation, and so the accelerations, how much does it speed up or slow down in this case per every second. And so the time took 5 seconds, so that starting velocity was 25 meters per second. All right, so by practicing these kind of problems, it'll help you better understand how to use a velocity time graph in solving your equations. It always has something to do with the area, which is the displacement, always has something to do with the slope, which is acceleration. Keep practicing and good luck to you.